So we're going to start a new topic today. Turbulence modeling. So we'll talk about turbulence today. Okay. So we'll talk about the physical mechanism. There are no sums involved. Questions. There are questions, but not like two numerical questions on these topics, right? So, but you will have workings on regeneration and so on. So, if you have seen a past paper, I'll put some. You haven't seen past paper, have you? So I'll put some past papers in here. So, how to do an iteration? You should know. We've done it as well. I'll put some past paper questions so you will know how to approach such a question. But as for turbulence, so you need to know the theory, and there will be questions based on the theory. So your exam will be, as you know, your exam will be 25% of the module, 75% is the course. Then we'll talk about how Reynolds average equations are derived, and then we'll look at how to simulate turbulence or modeling. Then we'll talk about laminar flow first, because that is where it all starts. So it's a steady motion. Do not change its time. The streamlines just follow the same pattern, and there is kind of steady turbulence as well. In a sense, you have similar pattern, but turbulence always have a random behavior. So if you look at particles, so that will move randomly, not due to a particular pattern. So. But if you take a particle like that, so you have a particle, let it move in a laminar flow, then you have a particle, you let it move in a turbulent flow. So this particle may still move in a certain direction ultimately. So if you have a pipe, you have a flow, you have a laminar flow, so the particle will move smoothly. If it is a turbulent flow, the particle will be there, so that is a pipe, so it will move just like that. So it has a mean flow and a random element to it. So don't think that particles, there will be particles like you have the mean flow, particles won't walk in a random walk upstream. That doesn't happen. There is a mean flow always, and a random nature to the flow of the particles. Yes? So you need to understand that it's not just a random walk. It has a mean flow element as well. So Reynolds, the guy called Reynolds, he performed this experiment. So Osborne Reynolds in the 1800s. That is his apparatus. So what he had was like a fish tank. This is similar to a fish tank. Glass on one side, or maybe two sides, and liquid. And he had this tube carrying water downstream. So and then he observed. Then what he did was he injected a tiny stream of ink to the flow, and so he was releasing ink at a very, very small flow rate, so that it would. So we talked about streamlines, straight lines, and so on. Remember? So, what is ink? Remember? It's a straight line, isn't it? So ink will represent a straight line. But in laminar flow, the straight line and the streamline are the same, aren't they? So he looked at the straight lines, and this is laminar flow. Yeah, very linear fashion. So you would see the mean flow in a linear fashion. And in transition, so it started laminar, and at some point it became erratic, turbulent. And turbulent flow, so it was all eddies. Yeah. So this is the experiment. This is what Reynolds showed in his experiment. So what he did was he measured the velocity and determined when the flow would become turbulent. Yeah. So so these are straight lines or streamlines for laminar transition and turbulent flow. So a feature of turbulence is like this is what I mentioned before. So you have unsteady irregular motion in which transported quantities are mass, momentum, and scalar species. Yeah, fluctuate in time and space. So if you look at the velocities, so that's your mean velocity. So that's your fluctuation. Okay, so your velocity at a point can be given as u plus u prime t. Yeah, so that's at t you give u prime t is the random component and u is the mean component, mean velocity. Then if you statistically average them, now mean of u prime t, if you calculate the mean of u prime t, what would you get?
The average velocity?
No, u prime t.
Wait.
What should you get? Yeah, u prime t, if you average it. That one.
Should be the straight line again.
Yeah, that means u prime t average of that would be
Velocity.
0, wouldn't it? U prime t would be 0. Yeah, so that is what you should understand. So the characteristic of the turbulent flow is the large eddies in the flow, they follow the mean flow. Yeah, and the small eddies they behave in a random fashion around the large eddies basically, right? So Reynolds number for external flows along a surface, your Reynolds number should be greater than 500,000 for the flow to be turbulent. Okay. And if it is around an obstacle, it should be, because with an obstacle, now suppose you have a smooth surface, yeah. So this flow will a flat surface. The flow will stay laminar for a very long time. But if you have an obstacle like that, just because of the obstacle, the flow will become turbulent.
So that'd be like a pipe. There'd be if there was a bump in the pipe or something.
Yeah. Right. So when you talk about external flows with an obstacle, so the flow will become turbulent at Reynolds number 20,000 rather than 500,000. Yes. So,
I don't know why. I thought laminar flow was like below 300 or something.
no, 2,300 is for internal flows. Yeah. So we talked about this one the other day as well. For internal flows, it will become turbulent fairly quickly because of the wall friction. Yeah.
What if it's an obstacle in an internal flow like that?
Yeah.
Pretty much the way.
Because it's an internal flow, you already have walls.
Yeah. What, and they count as obstacles?
So they are like an obstacle. So that is why such a low Reynolds number.
So what would an external flow along the surface, what would that be like? The sea or something?
Yeah, for example, if you have a flat plate,
Yeah.
and if you have a bump or a bar or anything,
Yeah.
A rock.
yeah. So the
Like a weir in a river or something.
sorry.
Like a weir in a river.
Yeah. So what happens is like you have a smooth flow over the plate, and then when you have an obstacle, the flow direction changes, doesn't it? So because of that direction of change of direction of the flow, there will be eddies created.
Yeah,
Automatically.
when the floor comes back and starts to
So that's why the flow will become turbulent fairly quickly. Yeah. So for natural convection, you define what is called the Rayleigh number. Rayleigh number is and then you have what are called the Prandtl number as well. Yeah. So Reynolds number is defined as RE equals rho u L over mu. So you know the critical Reynolds number. We talked about the critical Reynolds number earlier. So 10,000. So for external flows, it is 500,000. For external flow, it's an obstacle to 20,000. For internal flow, it's 2,300. Where it becomes turbulent. So the real mechanism of transition from laminar to turbulence is still unclear. Okay? So you can't really explain where it happens and you know when it happens, but how it happens, it's not explained properly yet. Widely accepted explanation is due to instability. You can explain it using energy theories as well. So in practice, what we do is we use the Reynolds number to determine the region. And so that would be a velocity. So now this is inviscid stability. This is viscous instability. So meaning even in an inviscid flow, turbulence will start. Yeah. So
Sorry, what was the y-axis on those charts? Yeah.
distance
Distance from the wall.
from the wall. So flows of interest, free turbulent mixing layers, jet flow, wake, and there are wall-bounded turbulent flow like pipe flow, flat plate boundary layer. So
Is pipe flow usually turbulent?
if the Reynolds number is greater than 2,300, it's turbulent. Otherwise, it's when you open your faucet at home,
Turbulent.
so when you open it slowly, the flow is laminar, isn't it? So
I'm only asking because that's my dissertation. I was distracted.
So like, is everything you've done wrong?
No, I'm done with it.
Alright. Can't be wrong.
so you know that there are some trucks with air, which draw air into the water flow as well.
No, we put air into the flow.
Yes.
It's not just a pump.
No. When you open the faucet,
Yeah.
there is a there is a hole in the backside of the tap,
And it just draws it through.
and it will draw air into the flow of water,
Yeah.
and it mixes water with air, and what you will get in your hand is a mixture of air and air.
That's
and
what
water.
becomes all bubbly.
Yeah. So that saves water, because most of the people, for example, when you brush your teeth and when you wash your mouth, you just open the faucet and do that, don't you? So not many people use a cup to.
I still wash.
Even when you wash your face, you don't
Still
collect water and wash it. You just open the faucet and naturally we like flowing water, because flowing water is more. Our instincts are to use flowing water than still water. And if you look for cats, for example, some cats, when you have still water for them to drink, they come and hit the water before they drink it. So they don't like still water, because still water can be stale, can have more bacteria than stagnant water. Yeah. So some natural phenomena. So now this is a boundary layer on a flat plate. So these are the pictures. Yes. So you can see that that's the fast stream, mainstream. So that's the boundary layer. So laminar, transition, turbulent. Yeah. So now these are the wave fronts. So this is at transition, and that's at that's the fully turbulent region. So there are 3D distortions starting here, and these are called hairpin vortices, and then these are turbulent spots, and these are fully turbulent eddies. Yeah. So this is again a structure, turbulent structure. So these are kind of laminar regions in a turbulent flow. So these are fully turbulent. And then we define some terms. U plus is the mean flow divided by the turbulent velocity. Mean velocity divided by turbulent velocity. Y plus is the mu rho. U turbulent y over mu. Yes. Then you define what you call the friction velocity, ut. That's the turbulent velocity. Then you have laws of law of the wall, velocity, deflected flow, etc. So delta is again the boundary layer thickness, basically. Yeah.
What does that mean though? U plus and Y plus?
Physical meaning is how much turbulence you have basically. Y plus is the distance from the wall to the turbulent layer.
And U would be the velocity.
Yeah, U would be the velocity, and UT would be the turbulent velocity.
Okay.
So, turbulent velocity profile near the wall. So you have the viscous sublayer buffer here.
Hungry with that guys.
Then you call it log-law region with viscous sublayer. So then it is the buffer layer, log-law region, and out layer of the wake region. So that's the those are the regions of the turbulent bound layer. Then you have a theory called eddy dissipation. Eddy dissipation means in a turbulent flow you have large eddies, okay? and the eddy breakup means those eddies will break into small eddies and small eddies and further small eddies. So when these eddies break up, what happens is the kinetic energy is transferred into thermal energy. Okay. So theoretically, your seashore, water and seashore is warmer than the water in the sea. Not just because you have the sand and the earth, because of eddy breakup as well.
Is that because it's more turbulent?
What happens with the waves is you have large waves and they are breaking into small eddies at the shore, don't they? So this is called vortex roll-up in a jet, then vortex bearing, and then these vortices will become large eddies. Yes. So this is called the energy cascade. So this was defined by the person called Richardson in 1922. So these are different types of flows. So that's a jet flow. Yeah. So this is the velocity profile of a jet flow. This is what we call a mixing layer. In a mixing layer, so that means you have basically no flow here. You have a flow there. So that mixes here. So it's like you have water and another flow of water coming over it. So then you have a mixing layer forming here. Yeah. And then you have a wake flow. Wake is something. Wake is you can consider it as an opposite flow to the jet flow, basically. So you have a mean velocity, and because of the wake, because of the obstacle, the velocity becomes zero in the middle. Yeah. Here, at the start, and then then you will have the mean flow at some point downstream. So numerical treatment of turbulence, how you numerically treat turbulence. So traditionally, CFD codes they don't consider transition. It models either laminar or turbulent flow. Because the transition, when you get a flow, usually the transition region is small. You can still ignore it. So, but you have some transition models here. So, especially when you use DNS, you can use transition flow if necessary. And governing equations. So these are the governing equations, not just for laminar flow initially, but then you define your velocity components with the mean flow velocity plus a turbulent velocity. Yes, and the other equations as well. So if you consider the Navier-Stokes equations like here, it doesn't consider turbulence, right? So turbulence has to be introduced into the equation. So how do you introduce turbulence into the equation is by having what you call you have what you call Reynolds averaging. So any quantity will have a mean quantity plus a turbulent or a fluctuating quantity as well. So in turbulent flow, variables change with time. Turbulent eddies are quite small. So if you were to catch turbulence, your grid has to be really small. Yeah. So and then you have what are called the mean velocities, and then you have what are called the Reynolds stresses. So you need the mathematical operations, divergence and gradient operators to calculate turbulence. So this is, you are not tested on this, so but this has been included for purpose of completion. Yeah. So this is the Navier-Stokes equation. If you include the velocity vector with turbulent component in it. So so turbulent model only deals with the momentum equation, because you introduce turbulent components in it, fluctuating velocities, and now once you've averaged, you have extra terms in the equation. Yes, so u prime bar, rho, v prime bar, etc. So these are called Reynolds stresses. So we have number of unknowns and number of equations. So now we have too many unknowns. So these are extra unknowns. Yes. So to close the extra unknowns, you need to have a model. You need to have an approximation for these unknowns. Yes. So that's what is called turbulence modeling. So what happens is, now if you look at this one, so if it is laminar, you don't have turbulent quantities, and you could solve it. But now you have more unknowns but the same number of equations as earlier. Therefore, you need to have an approximation for these to close the set of equations that you have. Yeah. So that is what is called turbulence modeling. Right?
How's that any different from like, so if you were to figure out the hoop stress or something, do you just add that together for like the total stress, or?
Hoop stress.
Say you were doing it in a pipe again.
Yeah.
So if you were to do like, would that just add on to all the other stresses it says, sort of going, is that only from the turbulent flow? It's nothing to do with like pressure.
Yeah, in the turbulent flow, what we define, okay, just take the velocity components.
Yeah.
So in the velocity components, you have a mean component and a turbulent and a fluctuating component. But earlier we had these velocities, and so those are the unknowns and a number of equations.
Yeah.
Yeah. So if you take a system of equations, if the number of equations, if the number of variables is equal to the number of equations, you can solve it.
Yes. But that's all stuff that like CFX will do for you.
Yeah.
So that's just in addition to the Navier-Stokes equations.
Yeah, when you write the Navier-Stokes equations for the turbulent flow,
Yeah.
you will add those fluctuating components in the equation as well.
Yeah.
So because you add those fluctuating components,
Yeah.
so those are new unknowns, aren't they?
Yes.
So therefore you need to get rid of, you need to have an approximation for those unknowns
Yeah.
as well. So that approximation is called turbulent fluid.
Are they pretty much like minimal, or is it, say like if you did like hand calculations and would you need to take that into account?
Yeah, like what the Reynolds stress is doing. It's not stress on the tube or the pipe, is it? It's
No.
stress in the flow.
It's stress in the flow. Yeah. Okay. Now I understand.
Sorry, yeah.
I understand what you're talking about. Okay. Right. So no. But again, the friction or the stress on the wall
Yeah.
will not be. So then you have to calculate the mean stress, don't you? So that will have mean stress. The velocity will have an effect on the mean stress. Right?
So, and that does affect the boundary layers.
Yes.
Right.
These elements are calculated in the iterations.
Yes. So when you say, okay, use K-epsilon turbulence model, that model will give an approximation for this one. So that is what we are going to talk about next.
As those approximations get better, so does your solution.
Yeah. So simulation approaches are numerical, direct numerical simulation. So if you use DNS, so you don't do approximations.
So that's a hand calculation, so
Yeah, you like hand calculations. Yeah. But if you were to do them using the computer, so the computational cost is prohibitive. Yeah, meaning too much computer power is needed. Then you call large eddy simulation. So here what you do is large eddies, you take the large eddies out of the flow. So if you are, for the large eddies, you don't consider them to be turbulent. Okay, so they have the mean flow velocities. Large eddies will have the mean flow. The large eddies don't move. Yeah, but the smaller eddies do have turbulent components. So with that, so this is not like so you do some of the calculations like DNS. That is for the small eddies, not for the large ones. Yeah. Then Reynolds average models. So here what you do is you average them. So solve time average Navier-Stokes equations. So all turbulent length scales are modeled, meaning you give an approximation for that all the time. Yeah. So Rand's or Reynolds averaged Navier-Stokes equations are the most widely used method. Yeah. So now this is what happens when you time average. Yeah. So that will be your mean flow. So that is what is the Reynolds average Navier-Stokes equations will give you. So so it will give you a mean flow picture of the mean flow, not the random components. Yes. So because of turbulence, you have the Reynolds stress, what you call the Reynolds stress tensor. So you solve, so this Reynolds stress tensor is modeled, meaning you give an approximation for that. Yeah. So closure means because you have the more number of unknowns than the number of equations, you need to close the set of equations. Then what you have what you call the Bosinesque hypothesis. In Bosinesque hypothesis, Reynolds stress are modeled using an eddy viscosity model. So you define the term called eddy viscosity, and with the eddy viscosity, using eddy viscosity model mu t, you can model the turbulent component. So still modeling is required for transport equations. Reynolds stress models or RSM is more advantageous in complex 3D turbulent flows with large streamline curvature and swirl, but the model is complex, right? So turbulence models, classical models are based on Reynolds average Navier-Stokes equations. The time average zero equation model is called the mixing length model, and half equation model is Johnson-King model. One equation Spalart-Almaraz and Boldin-Bath model. So two equation models are like K epsilon, K omega, shear stress transport, or Reynolds stress model. So you have seven equations. And then you have what you call algebraic stress models.
So in the coursework,
yeah,
they use K epsilon.
Yeah, because your flow is almost laminar.
Well, that's what I was about to say. These are turbulent models, right? But we want the flow to be laminar through the turbine, I think. So, or up to the turbine. So I guess it's supposed to be laminar.
Yeah, I mean, because you have a large variation in the area,
yeah,
the flow can become turbulent at certain parts, yes?
Yeah.
So that's the tendency. So there is no harm using a turbulent model. So if the flow is laminar, the flow will be laminar anyway.
So, yeah, because I've not done very much of this. When you use the turbulence model, it doesn't mean that it's going to assume everything's turbulent and not show you when it's laminar.
No. So if it is laminar, it will still not be laminar.
Model. Okay, right. Okay. I guess I've just got to run it a couple of times to see that, I guess.
Yeah, of course.
And that will be obvious when you put the streamlines on. That they will be.
Do a simple check. Do a pipe flow.
Yeah.
Switch the turbulence off and switch the turbulence on for a very slow speed, and you will see it.
Cool.
So these are the examples. So this is a pressure drop, separation, shear effect, recirculation, etc. For different types of turbulence. So velocity profiles, near mole velocity profiles. What you can do is actually you can use a predetermined profile for the wall region. Okay? So you know how it should be using a model. You can just use an equation for the wall, or you can use a lot of grid cells for the wall, so that the wall is resolved. Okay? So if you use a kind of profile, predetermined profile for the wall, you call it a wall function. Yes. So by doing that, what you do is you don't resolve the wall using grid nodes, but you use a small function. You use a function to determine the shape of near the wall. So this is what it is. Like this is if you use a lot of grid nodes and solve it. This is, so then what you do is you get the shape of that, write an equation for the shape, yes, and then not use many grid nodes and apply that shape to the near wall region. You will get the same result. Yes, kind of. So y plus is the distance to the nearest to the first grid node from the wall. Yeah. So to resolve the boundary layer properly, this your grid nodes should be within the boundary layer. Yes. So wall functions are not valid in the laminar region. So when flow separates, so this is what will happen. So these are wall functions are applicable if the wall flow doesn't separate, but if the flow separates, wall functions do not apply. You can't. So if you are looking at flow separation, you shouldn't use wall functions. So if turbulence is not directly simulated, that is DNS, turbulence transport properties are solved using K epsilon and K omega models. So like mass and momentum, turbulence variables also require boundary condition specifications. So turbulence intensity, just use 5% turbulent intensity if you don't have an idea. So nominal turbulent intensities range from 1 to 5%. Turbulent intensity means how much turbulent flow is, right? So default is 0.037, which is 3.7. That is good enough. Yeah. So then two equation models. The industrial CFD standard code ANSYS, you always use wall function. So y plus should be less than 300 for the wall functions to be used. There is no lower limit for y plus. So separation is under-predicted when you use wall functions, so definitely yes. So in K omega model, so K omega it resolves the boundary layer better than the K epsilon model. So very low y plus values can be used here. So to have a really good y plus value, you need to have a really refined mesh at the in here, yes.
But that's to find the y plus value. But then if you were using a wall function, then you don't need such a tight mesh.
Yeah, yeah. So that is what you are trying to do.
So you have to run a simulation to start, but is y plus an output of ANSYS? Or like
You can you can output y plus.
so you run it once to understand where the boundary layer starting and ending, and then use y plus in a later model if you want to say computer time.
Exactly.
Use the wall functions.
So shear stress transport models based on K omega model and has the same automatic wall treatment. So, shear stress transport model is good for good for separation. If you were to model separation, you would use SST model rather than the K epsilon or K omega models. Yes.
Do we need in our report we need to find y plus now?
Not exact.
No. So we're only using K epsilon model.
K epsilon models. So, but use boundary layer. You need to resolve boundary layer to get a good resolution, good answer for it. So, your y plus can be calculated or for using this equation. So that delta y is the actual distance between the wall and the first node. L is the flow length scale. Y plus is the desired y plus value. Reynolds number is the Reynolds number based on the length scale. Yeah. So with that you can calculate a y plus value. That is your first estimate. Yeah. Then the other models can be large eddy simulation, detached eddy simulation, and scale adaptive simulation. So this is out of scope of our module or exercise, but they are there for you to know that these exist. Mixing length models, the advantages are easy and cheap in the sense less time for calculations. Good enough predictions, not really good. So, but disadvantages are completely incapable of describing flows with separation and recirculation. You know what is meant by recirculation, yes? No? Recirculation means if you have a flow in one direction, if the flow comes back at some point, that is recirculation. Yeah? That happens in a jet, for example. You have a jet exerting material out of the jet, but at some point, some of the flow will come back. So that is called the recirculation.
Also like the eddies of the edge of the flow.
Yeah, the mean flow comes back a little bit, right? That is recirculation. So eddies, they will still have the mean flow direction, right? But if actually material is coming back a little bit, so that is recirculation. Especially in jets, you have recirculation, right? So, so this only calculates mean flow properties and turbulent shear stress. Yeah. So KF epsilon model advantages, simplest turbulence model. So if the flow is predominantly unidirectional, it's very good. Yeah. It's well established, meaning well tested. Disadvantages, more expensive to implement than the mixing length plan, but with today's computers you can use it. Poor performance in a variety of cases like unconfined flows, extra length strains or rotating flows. It is not good for rotating 3D flows or rotating flows. If it is not even good for really fully developed flows.
What if you were doing like even before when we did the non-Newtonian flow? Did you still use K epsilon?
Yeah.
We did it.
You use SST most of you guys.
I remember, I'm not sure we did K epsilon.
Because you wanted to resolve the boundary layer, so you use SST, I think. Reynolds stress advantages, potentially the most general of all classical turbulence models. Only initial and boundary conditions are needed. It's more difficult to implement, more expensive in the sense. Again, not good in certain cases, Reynolds stress also. Algebraic stress, very cheap, and it's only slightly more expensive than K epsilon. So we don't use this much when you have K epsilon. So the different approaches to turbulence are DNS, direct numerical simulation, most expensive. Reynolds average Navier-Stokes next, and LES, large eddy simulation. Then VLES, so it is for large external flows. DES, which is called the detached eddy simulation. So that is a combination of LES and Reynolds average Navier-Stokes modeling for the near world region. Yeah. So your model choices, use K epsilon first, and then maybe use SST. It's good to calculate, estimate the y plus value with the equation that was given earlier. If it is a swirling flow, make sure you use SST rather than other two, K epsilon or K omega. Yeah. So this is just a jet flow. for using different models. So that is those are the experimental values. K epsilon model, SST model, K omega model. So which is good for this type of simulation. Yeah. That ends the discussion of turbulence. So we will. You can continue with your assignment work. So I'll come and see you guys. I will be finishing lectures next week, and I have put all the material on Blackboard now.
The past papers.
Not past papers, but I will put the past papers as well. Yeah.
Wow.